I'll post an announcement. Okay. Announcement there. So let's try to remember what we were doing. Okay. We are, in this section, we're talking about limits as we approach infinity. So basically dealing with infinity in our limits. We said a strategy we can take. We want to know what our limit is as we approach infinity. It can be kind of tricky if we have a ratio, if we have a rational function. So the last thing we looked at is if we have one of those, and we can divide every term by the largest power of x we have in the denominator. And when we do that and simplify, then we had that special limit we can remember that anytime we have 1 over x to the r, as long as that power, that exponent, is a rational number, and then the limit as we approach infinity or negative infinity of those things, where we have something over a power of x, is going to be 0. And then we can figure out our limit from there. So then we would just have the limit of 3 and over the limit of 5, and that's just 3/5. And then we had one where it was a little trickier, because on the top we had a square root. So when our largest power of x in the denominator is just x, at x to the first. When we try to divide by that underneath the square root, we had to remember that square root of x squared is the absolute value of x. So in the case where we're dealing with positive x's, it's okay. It's just, we can call it square root of x squared. But if going on the negative side, we have to remember to put a minus sign out there. Here of the signs. We did those. We said we were finding horizontal asymptotes. Doing that, and we had last one was our graph of that last one. Said a few things. We said that as far as horizontal asymptotes, our graphs can have no horizontal asymptotes. That's okay. It's a lot of functions. Or they could have 1 horizontal asymptote, or they could have 2 horizontal asymptotes. And that was the max. Because if we have any more than 2, we start having problems with the vertical line test, and we don't have functions. Okay. So we can have 0, 1, or 2 horizontal asymptotes. That's where we made it to. And so not too much left in this section as far as lecture goes. Okay, the next little thing we're going to look at, it's got a lot of infinity thrown in here. I've got infinite limits at infinity. Okay. So what we're thinking about here, situation like this where when we try to find the limit of our function as we approach infinity or negative infinity, then we get infinity or negative infinity as our limit. So that's the case where we do not have a horizontal asymptote. Our function just either gets really big or gets really small without bound. Get those. So that's sometimes pretty straightforward. It's a little weird because infinity is not a number. Right? So sometimes it can make it a little tricky to think about. And then sometimes we can kind of get ourselves into sticky situations. We'll look at a few of those in our examples, but look at this one. So here we've got x to the third as our function. And we're going to look for the limit as x approaches infinity and as x approaches negative. So the extreme right and the extreme left for our graph. So if you think about what happens there, right, we're just cubing whatever our input value is. So the bigger our input value, 10 cubes 1,000, 100 cubes 1,000,000. The bigger our input value, the bigger our function value is. And it just keeps going that way. So there's no boundary on how big our functional value can get. if we keep making our x's bigger, our y's are going to keep getting bigger. And that's not too tough to think about. So as we go toward infinity, bigger and bigger and bigger numbers cubed, they just get bigger and bigger. So we would say the limit as x approaches infinity for x cubed is infinity. Have an infinite limit there. And then similar on the other side, if we're using negative values, the difference there will be our signs. So like if we do -1 cubed, we get -1. And so we're going to have negatives, but the magnitude of our number gets bigger and bigger. So we're saying we're going to get large negative numbers, and the more negative our x's are, the more large negative our y's will be. Well, we can see that from our graph too. So on our graph, as we go off to the right, we'll just go up without bound. We go off to the left, we go down without bound. So there, I didn't finish my thought there. We approach negative infinity, our limit is negative infinity, it goes down. Those you have to think your way through. You have to actually stop and think what happens if I plug in really big numbers or really small, really negative numbers. It's not quite as easy as direct substitution, because we can't like substitute in negative infinity to get negative infinity cubed. We can't cube negative infinity because it's not a number. We kind of have to reason our way through those. All right, but we can do that. Okay, we'll see a couple of sticky situations when we do some of our examples. How to work through that. That's the idea. That's the rest of the lecture. And so we'll just do some examples. Sound good? You'd probably rather be working problems than listening to me. Anyways. Done with the slides. So let's look at some problems. All right, so this one's a little different. It works out a little different than ones we've done so far. So let's find this limit. I find the limit as x approaches negative infinity of x minus 5 over x squared plus 8. So anytime you see a rational function, and we're looking at a limit as we go toward infinity or negative infinity, in our technique, we're going to take that largest power of x in the denominator, or largest power of our variable, x here, and divide every term by that. So if we divide every term by x squared, write it down if you need to. But if we do x over x squared, we're going to get 1 over x. And then if we do -5 over x squared, it's just -5 over x squared. If we do x squared over x squared, we'll get 1. If we do 8 over x squared, it's just 8 over x squared. That's simplified. So we're dividing everything by x squared. Okay. So then what happens? Let's take care of the 2 easy parts first. Well, really, we got 3 easy parts. Because what I'm thinking about is anytime we have something over a power of x, whether we are approaching infinity or negative infinity, what are those limits going to be? 0. Okay. So the limits of all three of those parts are 0. So what are we left with? Yeah, we got 1 on the bottom. And on the top, we've got 0. So what's our limit going to be? 0. Yeah, 0 over 1, so it's 0. Right, 0 over 0 is undefined. So in those cases, if we get a 0 over 0 situation, we have a name for that. We would call that an indeterminate form. So we would have to try to rewrite it algebraically or use some other technique to try to come up with the limit then. Yeah. We've run into a few of those, right, where like if we plug 0 into the denominator, we get 0, and then we have to do something else to figure out our limit. Okay. Got that one. Not too bad. Same technique. It just works out a little differently because everything in the top goes to 0. Okay. Let's try another one. Limit as x approaches infinity. X to the 4th minus 1 over x squared plus 2. That's a 4. So, same category of limits. So, same idea we used on the last one. Here, our largest power of x in the denominator is x squared again. It's not always. I'm going to divide everything by x squared. On the top, if we do x to the 4th divided by x squared, what's that going to leave us? X squared. And then we'll have minus 1 over x squared. Bottom, if we do x squared divided by x squared, we get 1. And plus 2 over x squared. So we've got two pieces that go to 0, right? The minus 1 over x squared, that limit is 0. The bottom, the 2 over x squared, that limit is 0. So what we're left with, a little different than ones we've done so far. We've got the limit as x approaches infinity of x squared over 1, or just x squared. What's that going to be? Infinity. Because what happens? We have to think our way through. Yeah. We technically can't just direct substitute, right? Because what's infinity squared? We can't carry out that operation. So we have to think through it. If we plug in bigger and bigger numbers for x, so we're squaring larger and larger and larger values, our function is just going to get larger and larger and larger, and there's no end to it. Okay, so yeah, our limit here would be infinity. Okay. Now, on these, it gets a little tricky when you're trying to answer a homework question. And I can't really find the rhyme or reason behind it in WebAssign when that won't which answer. But kind of when we're saying the limit of something is infinity, that's saying we really don't have a limit, right? Because it just keeps getting bigger and bigger and bigger, and it never quits. So some of the answer boxes, you can put infinity in, saying, yeah, it goes toward infinity. But then sometimes if we get this situation where our limit is infinity, it'll want D and E because we really don't have a limiting value. It goes forever, so we really don't have a limit. So if you try to put in infinity and it doesn't like it, try D and E. I wish I had a good thing to tell you on when it wants infinity, when it wants does not exist. Don't. Depends on how the questions are set up in WebAssign. Keep an eye out for that. Okay. Do one more of these. We've actually done one similar to this one before, but these infinite limits kind of break down into 3 types. So let's do one of these and then we'll see if we can make some observations. The limit as x approaches infinity of 3x minus 4 over 2x plus 7. Our largest power of x in the denominator this time is x. Divided returned by x. Okay, so 3x divided by x will leave us with 3 minus 4 over x. 2x divided by x will leave us with 2 plus 7 over x. Pieces with the x in the denominator. Those limits are 0. Now we got the limit of 3 over 2, which is constant. So what's our limit? 3 over 2. 3 over 2. Okay. So these 3 examples give us the 3 possibilities for how these turn out. We really only have kind of 3 cases. Okay, we have an infinite number of different solutions we can get for the limit, but we really only have 3 cases. We've got one like the first one, where we can end up with a limit of 0. When they're on the top, we get 0. We have cases like the second one, where we end up with an infinite limit. Or we could say the limit does not exist. It goes toward infinity. And then we've got cases like the third one, where our limit is some other number other than 0. On test day, I need you to show me this process where we divide by the biggest power of x in the denominator and get to the limit, because this is technically the process we're going through. But there's a little bit of a shortcut we can take so we know which one of these we're going to get. So let's see if we can pick up on what the situation is. On this one, where we get 3 over 2 is our limit, the situation is the polynomial on the top, polynomial on the bottom have the same degree. They're both degree 1 polynomials. So then what's our limit? Where does the 3 over 2 show up in our original? Yeah, it's the ratio of the leading coefficients. You get 3 over 2. So really you can, after you know that, you can look at this thing and say, well, they're the same degree, so it's going to be the ratio of the coefficients 3 over 2. Okay, I need you to be able to show me all this, but you should know ahead of time your answer is going to be 3 over 2. That's why I'm giving you the shortcut. The textbook doesn't even talk about this. other two cases, and well, let's look, since we'll just go backward. In this case, where we get an infinite limit or negative infinite, okay, it could go either way. If we were going the other way, it might potentially have negative infinite. What do you notice about the degrees of our polynomials we started with? Yeah, that's true, but even just their sizes, their relative sizes, is all we need. You don't think too hard. Which one has a bigger degree? The top. Yeah. The top is degree 4, and then the bottom is degree 2. So degree, just in case, that's the largest exponent on an x. That's the degree. So if the numerator has a larger degree than the denominator, this type of thing is going to happen every time, where stuff in the bottom cancels, and then we still have an x in the top. And then when we plug or think about plugging in huge numbers for x, we're going to get a huge number out of this thing. So then we'll end up with this either calling it an infinite limit or saying the limit does not exist. That's no big. That's degree. The numerator is bigger. And then first one we did, where we got 0, what do you notice about the degrees on that one? The degree of the bottom is bigger than the degree of the top. And if you think about that, we can make it make sense that we're going to get 0, because we're going to have some number on the top divided by some really big number on the bottom. The number on the bottom is always going to be bigger because it has a larger degree. So in the long run, as we go out toward infinity or negative infinity, the bottom wins, right? It's going to be something huge dividing something smaller on the top. So if you divide some number by something huge, you get a really tiny number, so the limit is going to be nice little kind of shortcut there. The degree on the top is bigger, infinity or DNE. If the degree on the bottom is bigger, 0. If the degrees match, it's the ratio of the leading coefficients. And that's even true when we have one like this one we did last time. It's a little bit harder to see because the top was under a square root. But if you think about taking the square root of that x, our degree is going to be 1 because it's the square root of x squared. So the degree on the top and the bottom match. So our answer was the ratio of the leading coefficients, square root of 2 over 3. Didn't work that. You do have to be a little careful. Sometimes going toward negative infinity, you'll get the minus sign in there. Because we could get negative square root of 2 over 3. Thinking your way through that one, okay, without doing the rewrite, here we would have ratio of the leading coefficient, square root of 2 over 3. But since we're going toward negative infinity, in the top, when we square that, it'll make it positive in the top. But in the bottom, it's not, it's just linear. So it would make it negative in the bottom. So positive in the top, negative in the bottom gives us a let's see what else. Let's do one like this. So one example of a stumbling block we can run into when we're dealing with infinite limits. Something like this. Okay, so we said we can't really do direct substitution with infinity because it's not a number. We have to just reason our way through them. So let's take this one piece by piece. Right, so if we take a really large number and we square it, we get a really large number. Multiply it by some number, still a really large number. Add some other really large number to it, it's still going to be a really large number. And even if we take the square root, it's still a big number, right, as we tend toward infinity. We can make it as big as we want. So just looking at that first term, this thing going toward infinity. We can make it as big as we want. Then we got a minus sign. And then when we look at the second term, what happens then is we go toward infinity. So we plug in bigger and bigger numbers for x. What happens to 6x is just going to get bigger and bigger and bigger. It runs away huge. So it goes toward infinity. So our limit should be infinity minus infinity. Okay? But okay, we don't know how to do that. Okay? It's not a number. Infinity is not a number. So we can't subtract and say infinity minus infinity is 0. That would be nice, but it's not. That's not valid, okay, because again, infinity is not a number. It acts weird, and infinity acts weird sometimes. So we can't just subtract. So what can we do? We used a similar technique. Let me zoom out. We used a similar technique. Let me get rid of these, get these out of the way. We can rationalize. It's a little weird because our radical is in the numerator, but we can rationalize the numerator, and that will help us. That may not be like the first thing that comes to mind. Okay? So that's fine. Okay? But if you get a situation like this, we could classify this as infinity minus infinity indeterminate form. And we've seen if we have 0 over 0 indeterminate form, the thing we should try to do is we should try to factor and see if anything will cancel out. So if we get an infinity minus infinity indeterminate form and we have a radical involved, the thing we should try to do is to try to rationalize. Okay, this one's a little messy because it's so long. If we can tiny it up a little bit. So to rationalize, when you've got two terms, you multiply by the conjugate. So the conjugate, what does that mean? That just means the sign between the two terms. What do we do with that? Change it. So we're going to multiply by square root of 36x squared plus x plus 6x over itself. 36x squared plus x plus 6x. And it's not as bad as it looks because we don't have to think about every little term as we multiply. Because the fact that we're multiplying by the conjugate means we can use a pattern to do the multiplication. Right? This is saying we've got a minus b times a plus b. How does that work out? Do you remember? That's the difference of two squares. So if we multiply two conjugates together, we're going to get the difference of squares. So on the top, we square the first term. Our first term is that square root. So when we square the square root, what happens? square goes away. Yeah, it cancels out. So we just get what's underneath. We get 36x squared plus x, and then minus the second term squared, so minus 6x squared. And if we want to, we can go ahead and square that. What's 6x squared? 36x squared. You got to square the coefficient in the x. So minus 36x squared over all that garbage just goes on the bottom. Really not that bad if you use the pattern. Why does that help us? Thirty-six x squared is cancel on the top. That's right. X. Now we'll go back to our roots on these. So we've got a rational function, infinite limit. So we divide by the largest power of x in the denominator. Let me rewrite this just to clean it up. You don't have to if you don't want to. So we divide by the largest power of x in the denominator. Which is x. Because we got square root of x squared, so x, or you can look on the 6x, we got x. But just, we do have to be careful on these because we've got that radical. In this case, because we're approaching positive infinity, we can say that. Because if we were going toward negative infinity, we would have to have the minus sign. If we divide everything, really what we're doing, we're dividing everything outside of the radical by x and everything inside the radical by x squared. So what do we get? So top divided by x over x is 1. Then 36x squared over x squared. X over x squared, 1 over x. And then on the outside of that, 6x is just not under the radical of 6x divided by x, so we get 6. And then this is a little different than what we've seen, but we can still use our rule. This term, you can use our continuity property and say we could move the limit underneath the radical and think about it that way. Or you could think about the power of x here we have. Remember, we can, as long as our power is rational, we can say that limit goes to 0. So here we've got 1, and if you think about taking the square root, that would be x to the 1/2. Do that. So that's still rational. So we're justified in saying the limit of this thing goes to 0. You can justify it several ways. That part's 0. So our limit is 1 over square root of 36 plus 6. Square root of 36 is 6, so long way to get there, but we get it. Anytime you have a rationalizing step, it always just makes things long. But if you remember that pattern, actually doing the rationalizing is not bad. But hey, that's 1 over 12 is very hard to get from infinity minus infinity. So that's, you have to be careful. We can't do arithmetic operations with infinity. Okay. If it's approaching negative infinity, then let's see. So when we divide, that's the only part we have to be careful on. We would have, so negative infinity would be okay here, but then we would have a minus sign there, and then a minus sign there, and we would have a minus sign on the top. So you just have to put the minuses in wherever you have a negative infinity that's not squared. So then how would that work out? This part would still be 36. This part we wouldn't care about because it goes to 0 regardless of whether it's in positive or negative. And then this part would be minus, so we would end up with minus 1 over 12. Good question. Make sure there's nothing else tricky in here. So just keep that rationalizing trick in the back of your mind. It comes up from time to time. What was the other thing we used that on? We used it on something. We had one where we couldn't do direct substitution, so we rationalized, I think. I think we were getting 0 in the denominator. Yeah, we had 0 over 0 in the determinant form. There too. Other questions on those? I think I only gave you one like that because they are long. You have to rationalize. All right. So Friday's a short day, but before we go, I got a little quiz. There's no points. We don't have points for quizzes in here. Okay. So it's just for me to know how you're doing. Okay. It's hard to get people to talk, so just for me to know how you're doing. Okay. It's just three limits. Okay. Nothing. It's not this stuff. Okay, because we hadn't finished this stuff yet, so it's the older limits. Okay. And again, it's no points, so no pressure. It's just do the best you can on there, just so I know where you're at. Okay, and that's it. When you get finished, okay, we're done for today. If you, so I made them half a page just so I didn't have to use much paper. If you need more scratch work, just flip it over and you can just scratch on the back. Again, it's low pressure, so. Yeah, I do have a calculator up here if anybody needs it. But I'll mark them up and give them back to you. That's fine. Take it with me. Yeah, on the way out, if you need it, I'll put this up.